In this video, I'll talk about what exactly is a proof. What is meant by a proof? We'll talk about, in general, ways in which we prove certain statements, and then we'll take a look at an example of a proof. So first off, what is a proof? Well, a proof of a statement, just by the definition in our text, a proof of a statement is a presentation of a logical argument, so often written down or in a video, some presentation of a logical argument that demonstrates the truth of the statement, right? So it's just some logical argument that establishes that the statement is true. Now, ordinarily, what exactly does this mean, right? This is very abstract at the moment. So what does this mean? This means produce a sequence of statements. This is what or maybe I should say, what does a proof look like? What does a proof look like? It looks like a sequence of statements that each follow from the previous statements. So follow, what does this mean? Follow. This means I've used some sort of fact of logic to get from one statement or a collection of statements to the next. That's what it means by follow from the previous statements, and which terminates at the desired conclusion. So this is what a proof looks like. It looks like one statement after the other, each statement following from those that precede it, and the last statement that we show is our desired conclusion. So the conclusion of the statement. So this is what it takes to prove a statement. Of course, this is makes it seem, I guess, kind of easy, right? It's simple to state what a proof should be, but in general, proof writing is kind of difficult. It's definitely going to take a lot of work on your part and on my part to help you understand how to prove things and to give you some techniques for proving statements. But it's important to keep these definitions in mind, in particular that every statement you make in a proof needs to follow from the previous statements, and oftentimes that should be explained why it follows if it's not obvious. So what do we use in a proof? So in general, lots of things are used in a proof to demonstrate that the statements follow from previous statements. And what kind of statements do we even use? So we use several different things in a proof. We use definitions of concepts. We use what are called axioms or principles. So these are statements that we sort of accept are true. We don't require a proof of axioms. We kind of accept that these are true. They're agreed upon by everyone that they should be true, and we can use those in proofs. As well as principles. We'll encounter some principles later, like counting principles that are just, they're demonstrated to be true. We accept them as fact. So you can think of these like facts that do not need to be proven. That is, we've sort of, as a community, already agreed that they're true. So we use those. We use assumptions. So we'll make assumptions during a proof. We'll see that in an example for proving implications. There's an assumption that needs to be made. And we can also use previous theorems. So that's why do we need to prove statements? Well, one, and possibly the most important, is that we need to be sure that a statement is true, right? Like if I claim something is true, I need to be able to demonstrate that. And that's what a proof is. It's a demonstration that a statement is true. Another good reason to actually prove things and to learn how to prove things in this class is that it's a really good mental exercise. It gets you in the habit of thinking logically and not making any logical jumps that haven't been verified or explained. And so in this way, you can, as you prove things, your brain will sort of rewire in a way so that you're thinking more logically in any math class or in any class in general, and later on when you go into your career, the fact that you've taken this class and learned how to prove things means you're going to be a logical reasoner. You're going to be much more logical about your reasoning. You're going to come to better and verifiable conclusions along the way. And then another reason why we want to prove statements are true is because, well, once we know that a statement is true and we've demonstrated that, then we can use that in other proofs. We can use previous theorems, things we've already demonstrated are true, to prove that other things are true. And so in this way, mathematics keeps building off of itself. You prove a statement or a collection of statements, and then you can use those to prove further statements. And so mathematics just keeps building on itself. It produces this body of demonstrable statements, right? Statements that have been proven to be true. And so we know everything that follows from those must also be true. And this is really what mathematics is. So, all right, so what are we going to be doing in this section? Well, we're going to be looking at techniques for direct proof. So we're going to look at direct proofs. This is sort of the most fundamental proof technique, and that's a direct proofs of statements such as for all x in S, R of x. So in particular, we're going to be looking at proving universally quantified statements, things like this. Now, oftentimes, and in general, or in this section, we're going to look at a lot of statements where this R of x is really an implication. Because a lot of statements in mathematics are implications, that if one thing is true, another thing must follow. That is, we're not showing that P of x necessarily is true, we're just showing that if it's true, then Q of x also has to be true. There's lots of statements in mathematics that are implications, and so we're kind of honing in on that. So we're looking at statements that look like for all x in S, P of x implies Q of x. So how to prove a statement that looks like for all x in S, P of x implies Q of x. Now this could be worded as let x be in S. If P of x, then Q of x. So think about what needs to be shown here. I give myself an element of S. I need to show that for every element of S, that if P of x is true, then Q of x has to follow. So that is, I look at an arbitrary element of my set, and I make the assumption that P of x is true. So to prove something like this, we'll assume that x is an S and P of x is true. So why do we get to assume that P of x is true? Well, again, we're not proving that P of x is true. We're not proving that at all. We're proving that if P of x is true, then Q of x has to follow. Remember that if the hypothesis of an implication is false, the implication is immediately true. And so in that case, if the hypothesis is false, if not P of x, well, then we're done. We don't have any work. We already know that this implication would be true in that case. And so the only real work that we would have to do is to show that if P of x is true, then Q of x is also true. So that means we get to assume that P of x is true and show, so assume these things and show that Q of x is true. This is the general kind of formula for any proof of this sort. For all x in S, P of x implies Q of x. Assume x is in S and that P of x is true. Take these initial statements, these premises, and produce a sequence of statements that follow from the preceding ones and terminate with the statement Q of x. So once we've established that Q of x is true, then we're done with our proof. So let's actually look at an example. And let's prove it to see how this works. So what I want to look at is this example, or result to prove. Let x be a real number if x minus 2 is equal to 0, then x squared minus x minus 2 is equal to 0. So let's look at the strategy here. We'll assume x is a real number, and we'll assume that x minus 2 is equal to 0. And then we're going to show that x squared minus x minus 2 is equal to 0 by making logical arguments or logical steps to get from one statement to the other. So this proof is really just going to have one intermediate statement. So look at this assumption we're making, x minus 2 is equal to 0. Well, this is going to imply that x is equal to 2, right? If x minus 2 is equal to 0, then x must be equal to 2. And then what I can do is, now that I know x is equal to 2, I can plug that into q of x here and demonstrate that it's true. So let's actually prove this now. Proof. Let x be a real number. Assume x minus 2 is equal to 0. Then, since x minus 2 is equal to 0, x is equal to 2. So, right, these words, we use these a lot in proofs. Then, so these are all saying that this statement I'm about to say follows from the preceding ones. Then, so, hence, therefore. These are all little connector words that inform the reader that what I'm about to write follows from the preceding ones. So then x is equal to 2. So x squared minus x minus 2 is equal to, well, x is equal to 2, so this is equal to 4 minus 2 minus 2 is equal to 0. So in particular, I've shown here that x squared minus x minus 2 is equal to 0. That's it. That's what I wanted to prove, that this was equal to 0. So again, this just had one intermediate step. X minus 2 is equal to 0. This meant that x must be equal to 2, and then that meant that this open sentence was satisfied. And so that's a proof. Now, this little thing I put at the end of the proof, this is called a tombstone, and it's just meant to signify that I've finished the proof, that I've terminated at the conclusion. All right, the rest of this video is for this section. We're going to look through several different examples of proofs, proving statements like this, and we'll see a few different techniques coming up. See you there.